did a PhD at Brown University with Mark Johnson, working on lots of Bayesian stuff. Has since gone off to Edinburgh, where she continues working on sort of both the side of early language acquisition, but as well as sort of just core algorithms for doing machine. So she's going to be telling us a bit about that type of work she's doing.
Thanks, Sharon. So as Aaron mentioned, I kind of have two lines to my research. One is sort of more on the engineering side of coming up with better unsupervised NLP techniques. This is a talk that is actually focusing a little bit more on the other side, about thinking about how we can use methods from natural language processing and speech technology in actually modeling what goes on or what might be going on in human language acquisition, and in doing that, hopefully trying to answer some questions about human language acquisition, trying to gain some insight into that process, but also, in addition to sort of answering those scientific questions, I kind of hope that this work also ultimately will lead back to better NLP systems as well. I'm actually here for the semester at Hopkins working on some things having to do with word segmentation and speech and things like that, but that's actually not what I'm going to be talking about today. So I'll be talking about some other work that I've done. And this is work on the sort of idea of bootstrapping in language acquisition. Bootstrapping is a word that probably all of you have used at some point. It's used also in natural language processing. I think when people use this word, they have different things that they really mean by it. And so I wanted to kind of go back and think about what does bootstrapping mean, what have people used this term for, and what do I mean by it. So within the language acquisition community, I think one of the first people to really make this word famous was Steven Pinker, who talked about what he called the bootstrapping problem in language acquisition. And by that, what he meant was a very specific problem of how children break into the system of syntax. So in his view, syntax is particularly difficult because it's a very abstract system and it's sort of recursively defined. So noun phrases are defined in terms of verb phrases, and verb phrases are defined in terms of noun phrases, and it's not really clear how the child would break into that system. So he proposed that the way that they do that is by using semantic information. So specifically by using information from the context that words are used in and so forth, they're able to learn something about the meanings of particular words. And then by using correspondences between those meanings and syntactic information, so for example, they might know that certain kinds of verbs like action verbs have particular thematic roles, and that those thematic roles map onto particular kinds of syntactic categories. So by using that kind of information, which he assumed to be innate, that they use that to break into syntax. So that proposal was then sort of became famous under the name of semantic bootstrapping, right? So the idea that you use semantics to solve this bootstrapping problem in syntax. But because of that, I think the term bootstrapping then sort of later became known as a way of breaking into a system, right? So we have semantic bootstrapping, but then people also proposed the idea of prosodic bootstrapping. So this is the idea that actually what you're using to break into syntax is something about prosodic information. Or going in the other direction, syntactic bootstrapping refers to the idea that we use something about syntax to learn about semantics. So all of these proposals kind of go on the assumption that the child either learns something or knows something about some linguistic system A, and then they use that information about A to learn about B. So it's kind of a unidirectional way of looking at bootstrapping. My view of bootstrapping takes some of this, but also has a slightly different perspective on it. And that's because I'm kind of using ideas that I get from natural language processing, machine learning, that it doesn't have to be a unidirectional process. So I would agree with these previous proposals that bootstrapping does involve a structured correspondence between different levels of linguistic structure. It could be a hardwired correspondence. It could be a learned correspondence. That's a question that we need to answer, hopefully empirically. But importantly, it doesn't have to be a unidirectional thing, right? So we know from machine learning that you can perform joint learning where you have multiple kinds of latent variables that you learn at the same time, and that's kind of a bidirectional bootstrapping process. So looking at it in this way, the kinds of questions that I'm interested in answering are what the nature of the correspondence is between different levels of linguistic structure, whether that correspondence is in fact learnable or whether we need to kind of hardwire it into the system, and also whether thinking about these things in terms of joint learning can help solve the bootstrapping problem or at least give us some new insights into what might be going on. Question already?
If you want one.
Yeah, that's fine.
I completely agree with your perspective on the bootstrapping in the language learning literature. That as machine learning people, we look at it and we say, this is just joint learning. If you learn something about syntax, that might help you in semantic. Sometimes it might go in one order and sometimes in another.
Yeah.
So I always interpreted those proposals to say, to be statements about the empirical course of learning, that most of the learning was, that they tended to get A first and learn B from it. Is that, and then when people are arguing about whether it's syntactic or semantic bootstrapping, they're talking about which direction it usually flows. Can we say much about that based on the empirical data?
That's a good question. I guess I don't know enough about there's arguments in both ways, which is why there's this argument, right? People, have shown cases where there seems to be, information going in one direction, and they've shown cases where it seems to be information going in the other direction. I think the problem is that it's actually often very hard to tell from the kind of fairly sparse evidence that we have, either from observational or, controlled experiments, whether it really is sort of mostly going one way or mostly going the other way. Although you may be right that it's a question of sort of the empirical data. But I think sort of still thinking about it as like maybe it's really going both ways all the time, and that's how we should be mostly thinking about it, I guess, is more the point that I'm trying to make.
So able to show that these things were happening at the same time.
Yeah.
The same kid within
one
lab experiment.
Yeah. Yeah.
And I would be surprised if that weren't the case.
Yeah, I would too. I think, it's just, it's hard to sometimes get that sort of empirical proof for things, but yeah. Okay, so those are the questions that I'm interested in. So what will I actually be talking about today? Sort of two lines of work. The first one dealing with the question of prosodic bootstrapping, and this is work that I've done with my former PhD student, John Pate, who's recently graduated and is now doing a postdoc at Macquarie University. And then the second part on what I'm calling syntactic semantic bootstrapping, precisely because it is, in fact, a joint model that incorporates both of those kinds of learning, with the intention of trying to kind of point out that these are not really opposing theories, but could actually be sort of unified. Okay, so just to give you a little bit of background for this idea of prosodic bootstrapping, probably most of you know that prosody refers to the rhythm and intonation of speech. You may be less familiar with the way that linguists often assume that prosodic structure works. So it's assumed to be a hidden hierarchical structure, so in the same way that syntax is a hidden hierarchical structure, but not necessarily entirely coincidental with syntax. So what I'm showing here are some prosodic parses of a hypothetical sentence here, annotated using a particular kind of annotation scheme called TOBE, which stands for tones and break indices. So what you'll notice is that the tones here are annotated as these L and H things with little stars and so forth. So those refer to the sort of prosodic intonational contour of the sentence. And then the break indices are the little numbers that are subscripted on the words in the sentence. And the way to think of a break index is it's basically sort of a perceptual, how do we perceive the sort of break between those words? So there's not necessarily a pause between words that have a prosodic break in between them, but there's some kind of sense in which perceptually it seems like there's a break. So words that have a 0 as their break index are basically clitic, so there's no break at all. And it ranges up to 4 here, which indicates that it's the end of an intonational phrase, which is the largest type of prosodic unit that we can have. So in general, what you need to know here is, so I'll be using these break indices in the remainder of the talk. I won't actually be using the tones. And also that the hidden hierarchical structure here tends to be a bit flatter than syntactic structure. It's not recursive, and so, as I said, it does have some correspondence with syntax, but it's not the same thing. Nevertheless, because there is this correspondence, people have proposed that this could be useful in learning syntax.
So just for those of us who don't think prosody all day,
yeah.
how would I read this? If I will like green eggs and ham, I don't know, I forget the tones, maybe I'm just thinking about the breaks.
Yeah, so there's sort of a somewhat larger break after I. There's not really, just, yeah, no particular break after will, a somewhat larger one after like, and so forth. So I guess green eggs after that has a somewhat larger break, potentially because it's sort of a phrase in itself, and so forth.
The subscript on the word tells you how much of a pause, for lack of a better word.
Yeah, as I said, it's not necessarily a pause, but
so
yeah.
The line could just be one without any gap.
Yeah. And there's various cues to these breaks, which include things, I mean, it can be pauses, but it can be things like duration, which is in fact what we'll be using as a measure of this acoustically. Okay, so what sort of evidence do we have for prosodic bootstrapping? Well, there's actually quite a bit of experimental evidence that suggests that this could be a plausible explanation. So, for example, we know that even newborn infants are already sensitive to the basic rhythm of their language, and they can distinguish that from other languages. By 6 months old, infants are able to use prosody to distinguish between sequences of words that are a constituent and that same sequence of words when it's not a constituent. Syntactic constituent, I mean.
Green eggs in your previous example.
Yeah, so if there was like a prosodic break between green and eggs because they happen to be part of two different syntactic phrases, then they can tell the difference between that and, yeah. And we also know that adults do use prosody to disambiguate syntax. So, for example, things like ambiguous prepositional phrase attachments. And they're also able to use it in laboratory studies of learning artificial languages as a cue to the syntax of that artificial language. So there's a lot of experimental evidence, but as far as I know, up until the studies that I'll talk about now, I don't think anyone has actually ever tried to model this computationally. So because we were kind of starting from this blank slate with computational modeling, we wanted to start from a kind of very basic sort of model. And so in our preliminary experiments, rather than trying to learn a hierarchical syntax, we started off by just developing a model that would try and learn syntactic chunks. So basically just figuring out, without any hierarchy, you know, what are the sort of most obvious phrasal constituents in the sentence. And to do that, because we don't need hierarchy, we can use models that are based on hidden Markov models. I won't go into the details of those. What I do want to talk about is just the kind of input that they used. So all of the models were given input which consisted at least of the words in the sentence. In addition, some of the models were given hand-annotated Toby break indices. So we got these hand annotations from the switchboard corpus. Yeah?
Before we go further, I don't want to push too hard on this, but do you have strong confidence in the Toby break concept where it's virtual, that is to say, where it's not actually instantiated by a clause? That there are
right. Yes, that's
confidence in those enough that you don't have to worry about that?
Yeah, that is an excellent question. And I think the answer for me is not necessarily.
Is it critical to the concept of rhythm in your last slide? Is the sensitivity to rhythm established on real empirical breaks?
No, I think that's not necessarily so the fact that infants are sensitive to rhythm could be coming from other things like, you know, the relative proportion of vowels and consonants in different syllables and things like that.
Does it rely on a Toby-based concept?
No.
Virtual break?
No. Yeah, so there is some debate about whether Toby is the right way of thinking about prosody. And so that is one potential. So basically, one of the things that I'll find in this study is that actually these Toby break indices are not as useful as just the other measure, which is just the raw duration measures. So one possible explanation for that is that Toby is just the wrong way of doing prosody.
Or that it's incomplete.
Or that it's incomplete, yeah. And there certainly are people who think that it's either wrong or incomplete. But not being a sort of theoretical linguist working on prosody, I can't speak to that. There are enough people who think that it's right that we thought, you know, we should give it a shot. Okay, so we're either using these Toby break indices or we're using just duration measures. So basically what we do is we take all the words in the corpus, we have a forced alignment with the speech signal, and we just measure what the actual duration in milliseconds of each of the words is, and we normalize that by the number of syllables in the word. Okay, so it's basically telling us, is this word longer or shorter than it sort of normally should be? And all of the models either get the indices in addition to words, or they get these duration measures.
That's right. You're doing that on the total length of the word, not on the final syllable.
Yeah, so actually in these experiments, we did use various measures and did some clustering. In the later experiments, we ended up just using the word duration because it turned out that worked just as well. Yeah. Okay, so here are some results of those preliminary experiments, and there's a few things I want to point out here. The first thing is, so I should say these are results on the switchboard corpus of spontaneous conversational speech. And there are two different models shown here. As I said, I don't want to get into the details, but basically the model that's shown in blue, the THMM, assumes that prosody and syntax are basically the same thing. So whenever you start a prosodic phrase, you start a syntactic phrase and vice versa. The other model, which you can see performs basically the same, doesn't make that assumption. It assumes that there are some probabilistic dependencies between them, but they're not really the same thing. But as you can see, it doesn't actually make any difference. The nice thing that we found is that when we add these additional sources of information, whether break indices or acoustics, we actually do get a benefit over the words-only baseline model. But as I said, we actually get more of a benefit from just using these word durations rather than the hand-annotated break indices. Okay. So altogether, the fact that, yeah.
This is parsing at this?
Yeah, this is basically we're comparing the bracketing F-score. So how accurate are the syntactic brackets that this model gets as compared to the gold standard parse trees. So the recall is really low because it's only doing chunking. And when I get to the full syntax model, we'll get higher F-scores. But that's why the scores are really low. Okay, so basically if you sort of take those results together, what we find is that acoustic information is helpful for learning syntax, but it's not obvious that prosody as such is what's going on. Because of the fact that we couldn't find any difference between these different model structures that treat prosody differently, and because we didn't get as much of a benefit from break indices. On the other hand, these were preliminary experiments. We were running them on adult-directed speech. We'd really like to be running on child-directed speech because it has shorter sentences, potentially simpler syntax, different prosody, and so forth. And also because we were running on these models that are not doing hierarchical structure, which is also kind of dumb for syntax. So in the next set of experiments, we were using a model that actually does use a full model of syntax, namely dependency syntax. So we have here a sentence where there are arcs shown between different words in the sentence to indicate that the word at the base of the arc is the head and the word at the pointy end of the arc is the dependent. And we're using this kind of model basically because most of the work recently in unsupervised grammar induction has been using dependency syntax as opposed to constituency syntax. So basically what we're going to try and do is, given a corpus of just the sentences, well actually the sentences plus either the break indices or the duration, can we get the model to actually learn where these arcs are correctly? So in order to do that, we use an extension of a fairly standard model for dependency syntax, and that's called the dependency model with valence. And the way that this model works is it's a probabilistic generative model. So it needs to go through and have a generative process for generating each individual sentence. And the way that it does that is it starts with the head of the sentence. It has some probability distribution over the heads. And then it's going to first generate all of the dependents to the left, and then generate all the dependents to the right. And then once it's generated all the dependents for that head word, it will then recurse and generate dependents for those words. So in this case, if we want to first generate some words to the left, we have to decide, first of all, are there any dependents to the left? Maybe there aren't any. In this case, we're going to decide, yeah, we need to generate something to the left, and we condition that probability on the head word itself, the fact that we're moving in the leftward direction, and what's called the valence, which basically is just the number of dependents that we've already generated in that direction, which in this case is 0. Once we've decided to generate that word, we then need to decide what the word is, and that again is conditioned on the head word and the leftward direction. In this case, maybe we decide, okay, that's enough. We don't need to generate any more dependence in that direction. And so we've generated basically, well, we have to probabilistically decide to stop. So in this case, we're generating something we call a boundary. And then once we've done that, then we continue in the rightward direction, decide to generate something, generate what it is, and so forth. So once we've generated a full sentence, that gives you a probability for the sentence. And using the magic of Bayes' rule, we can run some kind of inference algorithm. In this case, with the original DMV model, they basically just ran the expectation maximization algorithm and learn what the sort of optimal set of dependencies is for the input corpus. Now, we didn't actually use the EM algorithm, and we didn't actually use exactly this model either. And that's because this model assumes that you only have a single type of input, in this case, words. Actually, it turns out in the original model, they didn't even use words. They used parts of speech as the input. Whoops. So what we did use instead was an extension to this model called the DMV with backoff that was introduced a few years later. This was a model that allowed you to use two different kinds of input. So in this case, they were using words and part of speech tags and sort of interpolating between them using standard backoff methods. We didn't want to use part of speech tags, so instead we just replaced those with either the indices, the Toby break indices, or the discretized word durations. Similarly, we're not using exactly the EM algorithm with inside-outside, but intuitively, the algorithm that we're using is very similar. It's a variational Bayesian version of that that also learns the backoff weights at the same time. So using that model, we ran some experiments. We ran some, again, on the same switchboard corpus, part of switchboard that we had used before, because this is the only corpus that we actually have that has the Toby annotations in it. And we also ran experiments on a corpus of child-directed speech, which comes from the Brent corpus of Childis, and it's basically parents speaking to their young infants. And there's also recordings. So that corpus has a slightly larger number of sentences, but a slightly smaller number of words than the switchboard one, because each of the sentences is typically shorter. And John actually annotated the test set for this purpose. Okay, so what do we find in those experiments? Well, first I'm showing the adult-directed speech, and basically what you see here is more or less a replication of the kinds of results that we saw before. I have one additional line on here, which is the right branching baseline. So if you just attach everything to the right, we can see that as in other experiments with the DMV, we are outperforming that right branching baseline. And again, we see that adding acoustics to the model gives us a considerable benefit over just using words. In this case, interestingly, we don't even find any benefit at all from using the break indices. So again, we're seeing that acoustics are a lot better. We don't have break indices in the child-directed speech corpus, so I can't make that comparison. But once again, we see that adding the acoustics does give us a benefit in the accuracy of the dependencies that are being induced. So what happened to prosodic bootstrapping? Well, what we saw with both the hidden Markov models and the dependency model is that the duration measures were actually more informative than the Toby break indices. Now, I've already mentioned that one possibility is that maybe Toby break indices are just the wrong way of annotating prosody. That is certainly a possibility. The other possibility, though, is that maybe this isn't really prosodic bootstrapping. Prosodic bootstrapping, as we thought about it more, actually became less and less plausible to us as an explanation of what's going on in child syntactic acquisition. And the reason for that is that prosody is actually really complicated. And not only is prosody itself complicated, but the correspondence with syntax is complicated. And so it's not clear why, being able to use these two sources of information and then also having to learn this complicated correspondence would be a better way of doing things. Now, if that correspondence were something that were, universal across languages, then maybe, but it's not at all clear that it is. And in fact, even the correspondence between prosody and acoustics is actually very different between languages. So there's lots of ways in which this is complicated. Yes?
It's also the case that child-directed prosody is kind of sui generis. Maybe not even
Sorry, go on.
Prosody of child-directed speech may not be a reduced, but very closely patterned version of the kind of prosody, say, in school where between adults with low information transfer.
Right. So you're saying that there might actually be differences between child-directed prosody and adult-directed prosody, and so that would actually make it harder for the child to sort of, go. Yeah, so that's possible. I mean, I guess there's a question of sort of what's the continuity between the prosody for child-directed speech and for adult-directed speech. I mean, my feeling is that, like syntax, that it's not going to be entirely different. But yes, it may be that it tends to be somewhat simpler. And as you point out, obviously the acoustic realization of the prosody also has many differences because it's sort of there's much bigger pitch excursions and things like that. And that also kind of relates to the point here that, as I said, the acoustic realization of particular theoretical prosodic constructs is actually also different in different languages. So in some languages, break indices might be marked more by duration, and in other languages by, I should say, phrase boundaries might be marked more by duration, in other languages more by tone or something like that.
Cross-language similarity of child-directed prosody?
We know some things. Prosody in particular, I'm not sure. I mean, I think prosody in general is, I get the feeling that, my syntax is sort of where all the action is in linguistics. And I think it's partly because we started in English, and, syntax in English is very interesting. But, there certainly are people who are, looking at differences in prosody between, let's say, French and English in early perceptual learning, because, for example, French doesn't have word-level stress, whereas English does have word-level stress. And how does that affect things like, infants' ability to segment words from speech? So there's definitely work in that area. But I think, do we have a good grasp on, all of the possible universals and differences? No, I would say we do not. Okay, so I've sort of argued that maybe prosodic bootstrapping is harder than we would have thought before embarking on this whole attempt to implement it. So then you might have the question of, do I have some alternative proposal for why acoustics is helping us? And I do actually have an alternative proposal. It's, I would say, still a little bit in its infancy, so I'd be really interested if people have reactions to this. But the idea that we've actually been thinking about is the idea of predictability bootstrapping. And so what I mean by that is words that are spoken in more predictable contexts tend to be spoken with shorter duration. And there's lots of ways that you can measure predictability. One of the ways that turns out to matter is syntactic probability. So it turns out that there are experiments showing that if you have a verb like dance that can occur either transitively, like she danced the waltz, or intransitively, she danced, it tends to be used more intransitively. When people use that word intransitively, they actually give it a shorter duration than when they use it in the transitive frame. And vice versa for words that are typically transitive. So the duration that a word has actually could be giving you a direct cue to syntactic information. And we're exploring at this point the hypothesis that that might actually be something that would be useful for a child learner. As I said, this is in some ways, nicer than the prosodic hypothesis because it's this direct cue that's available and is sort of directly tied to syntactic probabilities. There's no additional hidden structure. And although this is an area, predictability, that hasn't been looked at much across languages, my intuition at least, and I would be thrilled if people started doing more work on this and showing whether this is true or not, my intuition is that there actually are going to be a lot fewer cross-linguistic differences in these kinds of effects. So again, it makes it easier to have sort of a universal thing going on. Yes?
So what is the purported universal generalization about the relation between duration and probability?
That words that are more probable are reduced phonetically. in this case, that since all we're measuring here is duration, that they should have shorter duration.
Enhanced is more often intransitive, but you might have
Yes.
some other word that undergoes such an alternation, like 8.
Which is more.
Other way around.
That's right.
And then it would be the intransitive form that's reduced.
Correct.
Okay. So this is not a cue about boundaries or anything like that. This is just telling you when a less probable frame for that word is being used.
Yes, at least in that particular. I mean, that's the experiment that we have that we can sort of point to. I mean, it may be that there are other ways in which syntax affects things as well. But yes,
right.
but from that particular experiment, yes, it's not giving you a cue to a boundary. It's giving you a cue to a syntactic frame. And in this case, that actually aligns nicely with dependencies as opposed to constituency structure, right? We have a model of dependency structure which basically says, you know, I should have some dependence in these two directions versus only in one direction.
And there is some evidence to support it. So zeroth order, if you say, okay, syntax, if you just look at which words get reduced most,
Yeah.
it's tied to the frequency.
N-grams. And frequency, yeah,
Unigrams,
absolutely.
Out of context.
Yeah.
Unigrams tend to, like, frequent unigrams tend to get reduced more often. You see all sorts of bizarre pronunciations for them more often.
Yeah. Yeah.
And I guess what you're saying here is this is a claim which sort of averages over other tasks that the procedure has to perform, like focus and things like that.
Yeah, so I think that's the potential difficulty of this explanation, is that there are other things going on as well, and how do you sort of control for all? Yeah, that's right. Colin. Yeah.
One about this one, do these durational differences that you point to in the verbs in particular, would those cross the threshold of your discretization? I mean, those seem very small to me. They might be at the level of 5 or 10 milliseconds.
Right.
They're not of the same type as the function word reduction.
Yeah, so the only thing I can say in response to that is that John has actually done some analyses where he's basically divided words into terciles. So, you know, basically short duration, normal duration, long duration, relative to their normal duration. And based on that division, it does seem to be the case that those correlate with being used in high probability or low probability dependencies.
The other question I had just really quickly, I guess you would ask me, how would exotic bootstrapping help control syntax in English? I would just say domain file length. It has to be domain file length. If you learn that words with the utterances are longer than they
Right.
would be otherwise,
Yeah.
then you infer that words are long at the end of syntactic constituents in general.
Right. So you're basically saying the intonational phrase is basically the only level at which it matters.
Domain final lengthening or domain initial strengthening of client levels.
Yeah. Well, okay, right.
So, yeah. So, is that how your models actually work? Do they use this domain final lengthening generalization?
They do not build that in directly.
Yeah, is that what they learn? Is that
Oh, right. So again, yeah. So again, John has done some analysis of this, and it gets a bit detailed. So I don't actually have slides for this in the talk because I was sort of hoping to like skim over this stuff. But it's an interesting question. So it's in his thesis. My recollection is that he found, strangely, no, that's right. I think what he found was that he did not get lengthening in the place that you would expect from domain final lengthening. What he was actually getting was some kind of informative cue that was happening at the beginnings of phrases, not at the ends of phrases. And of course, we were expecting the same thing that you said, and so we thought that was a little bit weird, which is part of why I didn't say anything about it, because I don't have an explanation for that. Anyway. Okay, so this slide is basically all the questions that I've just been answering about further analysis that we've done. And the only point that I want to make is that it seems like because of these analyses, we were able to do the same kind of analysis also in the words-only model, and we find these same kinds of correspondences, which also seems to suggest that this is a potentially learnable cue, because if you're not using that cue initially, but you see those correspondences, then you could sort of start to pick up on that cue and then use it in an informative way. Okay, so see John's thesis. And we're hoping to sort of build these into more robust analyses. Yes? Okay.
So duration is
Yeah. Yeah, so that's certainly a possibility, and we could try rerunning some of these experiments with some of the other kinds of information that's available in the Toby annotations. Yeah. Yeah.
The switchboard corpus in particular has one pitch accent mark for every major phrase or something.
Yeah, I think. Okay.
Jack paid for it, and I got it.
Thank you. That's good. Yeah, one more question, and then I'm going to really have to move on. That's okay.
You said earlier that infants just 4 days old were using prosodic information, and so I was wondering, like all of this seems to be to require you to know where the word boundaries are, and I was wondering if any of this information is available before the infant has done word information.
Right. So certainly at the point at which the newborns are kind of knowing something about rhythm, no, they do not have word boundaries. But similarly, as I said earlier, that rhythm that they're picking up on is not necessarily this kind of prosodic information. I think the question of how much of this is available before they have word boundaries is a really good question. I suspect that some of this sort of information is probably being used to find word boundaries in the first place. So, for example, the domain final lengthening, is also a cue to where the word is ending, not just where the syntactic phrase is ending. So I think there's I should point out, I guess, the 6-month-olds in that study where they were distinguishing between constituents and non-constituents, 6-month-olds can identify a very, very small number of words. I think it's almost impossible that they were actually identifying the actual words and segmenting the actual words that they were hearing in that study. So it seems to suggest that they can do something with prosody even before they have individual word boundaries available to them. Okay, so I'm going to move on. That's my summary, basically, that acoustics is useful, prosody may or may not be useful, and further analysis needs to be done. Moving on to the other part of the talk, syntactic semantic bootstrapping. So as I said, this is a model in which we're sort of trying to come up with a way of unifying these potentially opposing theories, which we do not believe are actually opposing. So I've mentioned a little bit about what semantic bootstrapping is. Right, this is the idea that children use word meanings to help learn syntax. And then the idea of syntactic bootstrapping, where children potentially are using syntactic frames to help learn word meanings. So the kind of experiments that you do if you're interested in supporting this syntactic bootstrapping idea is you might sit infants down in front of a couple of video screens, and on one of the screens there's a duck and a bunny, and they're both doing some weird thing, but they're doing it independently. And on the other screen there's a duck and it's doing something to the bunny. And then you present the kids, or you play for the kids sentences that say things like, look, the duck and the bunny are glorping. Or you play a sentence that says, look, the duck is glorping the bunny. And it turns out that in the case where you say the duck and the bunny are glorping, the kids look at the screen where they're doing something independently of each other. And when you say the duck is glorping the bunny, then they look at the screen where the duck is doing something to the bunny. So that seems to be evidence that they can use the frame in which you use the verb, this new verb glorping, to figure out what that actually means.
And then transfer the meaning of glorping to new situations.
I don't remember if that particular study has shown that. I mean, I think so. I've given you one of the earlier studies. There's later ones where they actually initially play the sentences without the videos and then do the videos afterwards, and to show that they don't need the stimulus initially in learning it. So I think that sort of gets to the question that you're asking.
And the concern is that when they hear the duck is glorping the bunny, they ignore the word glorping. They're not learning about the word meaning. They get it as the duck is doing something to the bunny.
Right.
And they pick that up.
Yeah. So this is, I think, one of the main criticisms of this proposal, which is that actually they clearly need to see. If you just play it in isolation without the video, then they don't really know the meaning of glorping. They just kind of know something about it. They know that it's a word that is a transitive verb and, has an agent and a patient and something like that, but they don't really know specifically what it means.
I'd be surprised if they hadn't shown transfer, though. I mean, like a whole line of work on this.
Yeah, I think so, but no? Okay. Oh, good. Someone who knows more about this than I do. Yeah. Right.
What the claim was that the syntax provided you the opportunity to learn the argument structure.
Yeah. Yeah. Okay. So, as I said, we have these sort of two different ideas about, what's being used to help with what, and the question is, can we come up with a way of sort of having a model that actually does both of these? And so we're going to do that using tools from the semantic parsing literature in natural language processing. And the way that this model is going to work is, as I said, simultaneously learning both syntax and semantics. When I say semantics here, what I mean is that it's going to be learning word meanings and doing that from sentence meaning pairs. And actually, to address Barbara's issue, we are assuming that because the sentence meaning pairs are available, that the kind of root meaning of the words is available in the context. We just don't know which part of the full sentence meaning goes with which word. So this is a little bit different from even from Steven Pinker's proposal, because Pinker's proposal assumes that kids are actually able to learn the meanings of individual words from the context, not just sort of full sentence meanings. The other issue here is that we wanted to use a incremental or online learning algorithm because we wanted to show something about the learning curves that the algorithm has and how those compare to kids. In the interest of time, I'm actually going to skip this slide. There are other models out there. I won't talk about them. What I do want to say is what is it that we're actually trying to learn here? So as I said, the input to this model looks something like this. So we have a bunch of sentences. Each of those sentences, in this case, I'm showing it paired with a single meaning. In some of the experiments, we actually pair each sentence with a relatively small set of contextually appropriate meanings, so there is some ambiguity. And what we want to learn as the output of the model is two things. The first of those is a lexicon in the formalism of combinatory categorical grammar, which I will talk about very briefly in just a moment, because I'm assuming not everybody here knows it. And that lexicon assumes that each of the items in the lexicon has a word form, a syntactic category, and a meaning. Once we have those lexical items, within this grammar formalism, it assumes that those items can combine with each other to form larger phrasal units and sentences. And in order to do that, because it's a probabilistic model, we need to have also a rule probabilities. So basically, with what probability do different words and categories combine with each other? Okay, so here's my really quick CCG tutorial. So as I said, the lexicon of CCG consists of items that have a word form, a syntactic category, and a meaning. Some of the syntactic categories are going to look something like ones that you might be familiar with from other grammars, like a noun phrase, in this case, NP. You might notice, though, that the word C here does not have a category called VP. In fact, the category for C is written as S\NP. What that means is it's a functional category which says I need to take an NP argument on my left, that's the backslash, and if I get that argument, I will return a sentence. Okay, and so what we see here in the bottom is actually that happening with the sentence UC. Okay, so basically C is combining with NP on its left and forming a sentence. And in addition, at the same time that that happens, the meaning of the word C, which is also a function, takes the argument of U and returns the full meaning of that sentence. Now, you might be wondering at this point, what happens if we need to use C in a transitive sense? This is only an intransitive. If we want to use C as a transitive word, we actually need another item in the lexicon that has another syntactic category. And that's the category of a transitive verb. Well, in English at least, it says I take a noun phrase to my right, in this case Alex, I combine with that, and then I return a category which requires an NP to its left, U, to form a full sentence. And similarly, the semantics also now requires two arguments. Okay, so given this kind of formalism, you'll notice that there's a very close coupling between the syntax and the semantics, and that's what we're going to be using in order to be able to learn these things at the same time. As I said, there's lots of ways that so in this particular example, there's actually very few ways that these words can combine to form legal sentences, but if you can imagine a very, very large lexicon, covering a lot bigger chunk of English, there's going to be lots of ways in different ways that words can combine with each other. And so in order to disambiguate and choose a reasonable structure for each sentence, we need to have probabilities on all of the rules that are telling us which things to combine with which things. Okay, so those are the things that we want to learn. The question is, how do we actually learn them? So let's imagine for a second that we have the lexical items. Okay, so if we have the lexical